Hi children, today I am going to start a very interesting topic, that is rolling. So we will see what is rolling, what are its kind and how questions are solved based on rolling, few constraints with rolling. All these things will be discussed today. So shall we start? Before starting rolling, let us first discuss this kind of motion, that is general motion of a rigid body. Now what do I mean by this general motion of rigid body? Till now we have been learning to analyze rotational motion of a rigid body about a fixed axis of rotation. Now if that axis is not fixed, it can also move in a plane, then what kind of laws can be written for that body? Of course, then we have to write both the laws. First will be for translation, that has to be summation of F to be equal to M into A of Cm in vector form, and other for rotation, that is net torque to be equal to I alpha. So we have to write now both the equations, translation as well as rotation. Now since we are writing the translation for center of mass, so second equation has to be applied about an axis that passes through center of mass. And since now center of mass is accelerating, so it will be a non-inertial reference frame. But even if we apply pseudo force, it will be at the center of mass itself, so its torque will be 0. So there is no need to apply a thing that is a kind of pseudo torque. It is not needed here, even if our frame is non-inertial frame. Now let us see what are the acceleration and velocity of a point on a rigid body. So first let us draw the conditions for a rigid body. Let this be a rigid body which is rotating about this axis omega. If this be the point of our discussion, let that be O, which is center of mass, and let the velocity of center of mass is in this given direction. Another point I am considering here, and with respect to O, it has position vector as RAO. See, as we consider the motion of A with respect to center of mass, then it can be seen as rotating about center of mass. So from here we can write velocity of A with respect to center of mass as omega cross RAO, because to center of mass this will be seen as rotating about it. So we can write directly the relation for rotation. And from here VACM can be written as VA minus velocity of Cm, that has to be equal to omega cross RAO, which will give then VA to be equal to VCM plus omega cross RA. This is how velocity of any point A can be described. It has to be equal to velocity of center of mass plus omega cross RAO term. Here the first term is corresponding to translation of center of mass, and the next term is corresponding to rotation with respect to center of mass. If I differentiate now the whole expression, that will give acceleration of A to be equal to ACM plus d by dt of omega cross RAO, which can be written as ACM plus alpha cross RAO, because here both the terms are variables. So first we have to differentiate one, taking other as constant, and then doing the vice versa. So it has to be alpha cross RAO plus omega cross VACM, which is differentiation of RAO with respect to time, and it can be written as ACM plus alpha cross RAO plus omega cross. Now VACM just now we have derived to be equal to, it can be written as omega cross RAO. Now as you can see, this is omega cross RAO, so this should be 0 because they are in the same plane, so cross product has to be equal to 0. From here we got final relation to be equal to AA can be written as ACM plus alpha cross RAO, which is our desired result. So these are the things first we have to know before starting rolling, because now the motion is not only translation, not only rotation, it is combination of these two kinds of motion. This is known as general motion, but it is possible only for a rigid body, which is not possible for a particle which cannot participate in rotation. Now I am coming to the kind of motion that is rolling motion. Now this rolling motion is a special case of combination of rotation and translation, especially if it is a pure rolling motion. So now this rolling can be written as this is translation plus rotation. Have you seen a bicycle when it is moving along a straight track? Here the center of rotation is not fixed, because for the wheel, the whole wheel, though it is rotating about its center, but center also is translating. So this kind of motion is called rolling. Here two things are involved. For center of wheel, it is moving forward and is in pure translation. But if you concentrate on a rim on the wheel, this traces out very complex path, which is a kind of translation and rotation about center of wheel. So let us see how this kind of motion can be analyzed. Now in general, if you consider motion of a rigid body, let that be here, which is in rolling. At any given instant, let A be the point here, and after some time this A has come to this location, which I am denoting by A dashed. Earlier this was the position of A, so it has turned, as you can see, it has turned by this much of angle, let that be theta. It is rotating in the shown direction. Now what about the center of mass? Center of mass has traveled a distance, horizontal distance, let that be S. Now if I write this, S can be written as r theta, because as the body is rotating through angle theta, its center of mass has to move by distance r theta. So I am writing S is equal to r theta. Now if I differentiate, what is this S? It is displacement of center of mass. So if I differentiate, it will give VCM. VCM is equal to ds by dt, that can be written as r d theta by dt, which is equal to r omega. So from here we got VCM to be equal to r omega. Similarly, if I differentiate it again, ACM can be written as dVCM by dt, that will be equal to r d omega by dt, which is r alpha. So we got these two relations. VCM is equal to r omega and ACM is equal to r alpha. And from here we can now express rolling motion as a combination of translation plus rotation. Now what about the speed of other points if it is in rolling? So let us consider this body which is rolling on a given surface. Now for center of mass, if it is rotating, if it is translating towards right, so it can be written as VCM. As center of mass is translating, so of course with that center of mass, all the particles, let us consider these particles. I am now denoting the points A, B, C and D. These all will translate with center of mass with the same speed VCM, because all are the parts of this rigid body. So all must be having the same translational motion. Now what about if we consider only rotation? This was pure translation where center of mass and along with this the whole body is translating. Now if we consider rotation, then of course all the bodies will be rotating with respect to center of mass. So if this be the center of mass, now we are studying motion with respect to center of mass, so it has to be at rest. The body is rotating in clockwise direction. Then again for these points, I can show here the points are A, B, C and D. What their velocities will be? At B it has to be in this direction, magnitude being equal to r omega. For A it will be in this direction, again magnitude by omega r, here also this omega r, and at this point also it is omega r. So all these points are now rotating, having their linear velocities that is equal to omega r about the center of mass. So this second figure corresponds to pure rotation. The first one was pure translation and now it is pure rotation. And the result is, I am adding these two motions now, so result will be that of rolling. Again, now denote the points A, B, C and D. Now if I want to show the direction of velocity for these points for center, it has to be VCM. What about A? For A, this is VCM and this is R omega. For D, it is this value omega r and here VCM. For C, it is both omega r and VCM in the same direction, and for B, this is VCM and this be direction of omega r. Now let us concentrate at this point, which is point A, that is in contact with the surface on which the body is rolling, because we know that if there is no slipping, then we can write VCM to be equal to omega r. Just now we have derived it. So what about A? Velocity of A will be equal to 0. It is very important concept, because the point for which linear velocity is equal to 0 is known as instantaneous center of rotation. So this is very important point known as I-core, which is instantaneous center of rotation. In some of the numericals, we are going to use this concept, that is concept of instantaneous center of rotation. How would you know which point is instantaneous center of rotation? It has to be a point for which relative velocity with respect to the surface will be equal to 0 if it is rolling on a surface, and if relative velocity is 0, then that point is known as instantaneous center of rotation. Let's proceed now. One example here I am taking just to illustrate it. Now if we consider a rolling body, let this point be P. Now we know that instantaneous center of rotation has to be here. So this is our instantaneous center of rotation. I am denoting by A. Now if it is this being the radius r, now position of this P, if it is making some angle theta with radius vector and this position vector being equal to r. Let us extend this and then draw a perpendicular here. So velocity of P has to be in along direction of this perpendicular, because now this is instantaneous center of rotation. And what is center of rotation? Center of rotation is a point for which linear velocity is equal to 0. So now we can consider that all other points are having velocity in a direction such that they are rotating about I, because I has no velocity of its own. So all the points now are in pure rotation about I. That is why always P has to be velocity that is perpendicular to the position vector of P with respect to I. This is the concept of instantaneous center of rotation. And from here now we can write Vp as well, because Vp has to be equal to, now as you know, this length can be written as 2r. So Vp can be written as r into omega. What is this r? This r is position of P with respect to I. And from the geometry we can write this r to be equal to 2r cos theta multiplied with omega. So we got the final result, that is 2 omega r cos theta, which is 2v cos theta, where v is actually velocity of center of mass, that is equal to omega r. Now we can write velocity of any point, because The only thing that we have to know is what is its position with respect to center of rotation, and then we can write its velocity. What will be about this point? If I consider this point as A, it will be having velocity. Just substitute here, that is 2v cos theta, and theta, if the point considered is at A, will be equal to 0. So velocity of A directly now I can write as 2v, because cos 0 is 1. What about this point B? Again consider R. This has to be equal to, now it will be 2v. What is cos theta here? As this is R, this also is R, so angle has to be equal to 45 degree, and we will write this cos 45, which is equal to 1 by root 2. That will give the value to be equal to root 2v or root 2 omega r. In this manner, now we can write velocity of any particle, acceleration of any particle, because these particles are now in pure rotation about instantaneous center of rotation. So according to our convenience, we can apply any concept. Either it can be motion of center of mass and rotation about center of mass, or it can be as direct rotation about instantaneous center of rotation. Then there is no need to apply motion of instantaneous center of rotation, because it does not move at all. This is the concept of instantaneous center of rotation, which will be very useful in solving questions. Let us solve one example. A rolling object rolls without slipping down an inclined plane where angle of inclination is theta. Then the minimum acceleration it can have is. To solve this, let us first draw the situation. It is the inclined plane having inclination theta on which a rolling object is placed. What forces will be here? The only force has to be weight, mg, which will have a torque about the point of contact, because other force that is passing through the point of contact itself will be having normal, and this cannot have any torque about the point of contact. So if we write torque about point of contact, the only force will be the force which is weight of the body. And then on writing the force equation and the torque equation, we will get acceleration to be equal to g sin theta divided by 1 plus I by mr square, which is a very standard result. You all must be familiar with it. And if A is minimum, then I has to be maximum. So minimum acceleration has a condition that I has to be maximum. Now I will be maximum only for the rolling object that is of the shape of a ring. So for ring we can write I max, which will be having value mr square. So if we put mr square in the above expression, A will come out to be g sin theta upon 2, which is our option number C. Now different kinds of rolling can be there. First, it can be pure rolling. As till now we had discussed all the cases were only pure rolling. So here I am drawing different cases so you can visualize what kind of rolling is pure rolling and what if it is not pure. So let us consider this body is rolling on a horizontal surface. I am considering a particle P here. It is the center. After some time, the center has moved to this distance, and now again P has come to the same position. Now what would be the motion for center of mass? It has to be along a straight line. But what about the path of P? Path P must have come to this point, then again reached maximum height, and then come here again and then reached again to this. It must be like in this manner. What about these 2 points? Distance about these two has to be equal to, because these 2 points constitute one full rotation. So between these 2 points S has to be equal to 2 pi r. And if it is a pure rolling, we can write motion of center of mass has to be equal to 2 pi r for one full rotation, and velocity of center of mass can be written by omega r. This is the condition for pure rolling. Now what if rolling is not pure? Then it is called impure rolling, or it is called rolling with slipping. So next I am going to consider rolling with slipping. Now for this there can be two different cases. In first case, if I consider again this rolling body on the surface. Now if this S, earlier it was equal to 2 pi r. What if this is greater than 2 pi r? Then we cannot write V to be equal to omega r, because velocity of center of mass, if it is omega r, in one rotation it has to move distance 2 pi r only. This time it is more than 2 pi r. So velocity has to be more than omega r, or we can write this to be not equal to omega r. Then of course the distance travelled will be more than 2 pi r. So this is called rolling with forward slipping. Whenever the distance travelled in one full rotation is more than 2 pi r, then it is known as forward slipping. This you must have experienced when friction on the road is less, that is in a rainy season. Generally motion of wheel on the road is not pure rolling. It is always forward with slipping. When you accelerate your vehicle, always that kind of rolling of wheel is rolling with forward slipping. And when brakes are applied, that is known as backward slipping. So for backward slipping, this S has to be less than 2 pi r. So this time if it is S, it has to be less than 2 pi r, or we can say that VCM is less than omega r, and of course it won't be equal to omega r. Right? So these are the different cases of rolling with sliding or slipping or skidding. But in our syllabus, the numericals will be only for pure rolling. So we have only to know about conceptually what is rolling with slipping. The numericals has to come from pure rolling itself. Now let us discuss problem solving strategy. How we have to attempt a given problem from rolling. So what the things have to kept in mind has to be, first we have to draw FBD. As in case of translation motion, here also we have to draw first FBD, because all the forces when shown, then only we can write laws of motion for translation as well as rotation. The second thing is, after drawing FBD, of course we have to write net F to be equal to mass of body multiplied with acceleration of center of mass. And this time while we are writing this equation, do consider our body to be like a particle mass only. While we are writing F is equal to ma, shape and size is not considered at all. So this equation corresponds to only point-like masses. So this will be our next step. And the third step will be, of course, since it is a rolling, rotation has to be involved. So we have to write equation of torque. That will be equal to acceleration of body with respect to center of mass into alpha, because already we have written acceleration of center of mass. So now rolling can be assumed as translation of center of mass plus rotation with respect to center of mass. That is why next step has to be writing torque to be equal to ICM alpha. This time we have to ignore translation of center of mass. The next step we have to consider is that we have to write no slipping condition. So directly you can apply ACM is equal to alpha r or VCM is equal to omega r, because it is not in our syllabus, so it will not be given in a question. Always we can consider this no slip condition. And then the last step is, the most important is, we have to solve all the equations to get the variable. Solve equations to know the unknown, whatever is asked in the question. So these are the strategies you have to follow while solving a problem that is based on rolling. Now I think you must be comfortable with all the concepts that will be useful for problem solving, and in the next session I am going to solve a number of examples based on the concepts we have learned today. Again, I am summarizing the concepts. First, it was rolling. Of course, before that, in last session I had discussed about constraint relations also, so that also has to be kept in mind. And the next term will be rolling. You have to consider as pure rotation about instantaneous center of rotation, or rotation about center of mass, and then translation of center of mass, whichever is convenient in any given problem, so that we will apply based on the situation. So let's wait for the next session where actually we will solve so many examples from this chapter. Till now, goodbye.